Hi. So now we're going to look at calculus, and this should probably be your first video within this topic, and that's going to be on limits, okay? And that's going to be the background behind one of the most important concepts, or pretty much half or all of this calculus topic. So you may have heard of limits before in IB, and especially if you've been quite rigorous in your learning. It's not a massive problem if you haven't heard of them or only heard about them in passing, seen the notation a couple of times. We will explain that now. Okay, so where could you have seen these limits being spoken about? Well, the first one we're going to talk about today is asymptotes. Okay, an asymptote is basically just a limit. Okay, a limit of a function. Okay, so what I've got here is any random function, okay, that has a horizontal asymptote. Okay, and as normal, okay, this line will be tending towards this dotted line y equals 2. Okay, and you may have used language like it gets closer and closer to the asymptote but never touches it. Okay, it gets infinitely close to it. Okay, and that's the language that you're going to see quite often in limits. Okay, but what's really happening here, or what notation should we be using for this asymptote? It's going to have some special notation that we see here. Okay, we've got lim f of x, and we've got a small x tends to infinity below it. So, what does that mean? Well, lim means simply the limit of something. Okay, the limit of. Okay, but it means the limit of, well, the thing next to it, the limit of f of x in this case. Okay, and so what is the limit of f of x? Okay, and this little writing underneath means as x tends to infinity. Okay, as x gets infinitely big. Okay, as it's getting bigger and bigger towards infinity. Okay, so in this case, in this example, well, what is the limit of this function f of x as x gets really big in the positive direction, as x tends to infinity? Well, the limit is 2, okay, as we know, okay, because the asymptote is at y equals 2. Next, we have geometric sequences. You may have seen them used here, and specifically used in the infinite geometric sum, okay, the sum of infinitely many terms. And well, hopefully, yeah, you've seen that limit notation used there as well, but again, your teacher may have skipped that to try and simplify things. It's not a huge problem. So can we use the infinite geometric sequences here, that formula? Yes, because the common ratio is less than 1 in this case. Okay, we have this formula, u1 over 1 minus r, okay, and your knowledge might be limited to how to use that formula. So we plug it in, 12 over 1 minus a half, which is 12 over a half, which is 24. Okay, so the sum of infinitely many terms in that geometric sequence would be 24. Okay, but again, what has really happened here? What notation should we be using if we're being properly rigorous? Well, what we're actually saying is, what is the limit of this sum? Okay, so the limit of this s of n, the sum of n terms, as n tends to infinity. Okay, because you can't really just add up infinitely many things. That doesn't actually make sense mathematically. Okay, but we can just say, what does it get closer and closer to as n just keeps going on forever? Well, if we start adding up, we get 18, 21, 22.5, 23.25. If we kept going, you'd see quite quickly that it would get to 23.999, and it tends towards 24. It never reaches 24, it gets infinitely close to 24, but we say the limit equals 24. Okay, we don't say that it tends towards 24. Okay, that is the limit. Okay, now we can see just a couple of ways of evaluating the limits themselves, again, not in the context of any sequences or asymptotes or any other topic. Okay, just simply what is the limit of this rational function, x plus 1 over 2x, as x tends to infinity again. Well, what we can do here is we can see some properties of limits. But first we can plug in a couple of numbers. If I plugged in x equals 10, I get 11 over 20. If I plugged in x equals 100, I get 101 over 200. Okay, and you might see sort of what fraction this is getting closer and closer to. But let's use some proper rules, properties of limits. So we can change this fraction here to x over 2x plus 1 over 2x. Okay, and we can actually just take the limit of both of those separately. Okay, so the limit of x over 2x plus the limit of 1 over 2x, and you are trying to write your x tends to infinity every time. You might get lazy, but try not to. So how can we evaluate both of these? Now, firstly, we can just cancel these x's in that fraction and be left with 1 over 2, 1/2, as x tends to infinity, and we'll come back to that. Then, how do you deal with 1 over 2x? Okay, as x tends to infinity, what does that fraction equal? Or what does it go towards? Okay, what does that tend towards? So 1 over 2 times something that's tending to infinity, okay, which you can almost think of as just 1 over some huge number that's getting bigger and bigger and bigger, okay, and if you looked at the decimal version of that fraction, that would be just tending towards 0.000, it would just be tending towards 0, okay, and we say that that limit equals 0, okay, 1 over infinity essentially equals 0. Okay, then we go back to this limit of 1/2 as x tends to infinity. Well, we have no x there, so that as x tends to infinity is almost irrelevant. Okay, that literally just equals 1/2. Okay, so that rational function, if you kept on going, is actually just tending towards 1/2. Okay, and we can see this with these plugging in numbers. If we plugged in 2, that would be 0.6. Okay, and then we've got that other one, 11 over 20, that's 0.55. Then that last one there, 0.505, I think. Okay, and you can see that that's tending towards 0.5. Okay, as we've shown with proper limit properties already. Okay, and finally, for this video, we're going to see how we can just use factoring. So I've got x squared minus 1 over x minus 1. I can factorize that to x plus 1 times x minus 1, and we cancel. Okay, and another thing to note here is that I haven't got something that tends to infinity this time. I've got something tending towards 1. Okay, you could have something tending towards 0 or infinity, those are the most common, but it could tend towards anything you want. For example, 1. Okay, so what's the limit of this function? Just x plus 1, a simple function, as x tends towards 1. Okay, well, in something so simple like this, you can use direct substitution. Okay, you can substitute in 1, essentially. Okay, it's as simple as 1 plus 1. This will just equal 2, as x tends towards 1. 1 plus 1 equals 2. Okay, so that's some background behind limits. That's going to be very important for the videos to come in a second. If you go to the next video, you'll see how that's relevant to one of the first things to learn in calculus.